welcome our speaker, Mr. Ajit Meghith, EVP of AI and Chip Engineering at NXP Semiconductors. Mr. Ajit Meghith will share his insights titled Scaling Intelligence, the Power of Right-Sized AI at the Edge. Ladies and gentlemen, please welcome Mr. Ajit Meghith.
Hello, everyone. Great to be here. The headlines in the tech industry these days are mostly about massive AI models or power-hungry compute systems that are typically designed for data centers or humanoid brains. At NXP, we'd like to look at the problem very differently. For AI at the edge to be truly transformational and impactful, the AI needs to live amongst us. It needs to be in everything that we use and work with. It needs to be executing where the data is born. So today, I'm going to talk to you about the transformational power of the right-sized AI at the edge. So we are at the precipice of ubiquitous AI. This is where AI becomes a seamless day-to-day companion for us. The possibilities are immense, but for this to be a reality, it's about how these AI solutions need to show up in the systems that we use. Whether they are deployable at scale, whether they are, the compute costs are manageable and sustainable, and whether they are built modularly so they can be upgraded and maintained over time. Before we get into the challenges of how we deal with ubiquitous AI, let's dispel one of the myths that is prevalent in our industry. So we typically talk about TOPS as a measure of compute power for AI. And I want to argue that more TOPS is not more value, especially at the edge. And in the last several years, we've been dealing with an arms race of putting bigger and bigger TOPS numbers in our data sheets. And we always find that the true value at the edge is about how AI performs, the efficiency at which it's performing, the utility value it brings, and the cost effectiveness of the solution that we're building with it. So it's very important to think, as we build these systems, are we building the right amount of compute power needed to make these solutions work? Now, if you look at the diversity of solutions at the edge, you have the data center on the far right. This is where the data is usually, the models are usually generated and trained. But the rest of it, we call it simply as the edge. But there's a huge diversity here. You look at a healthcare monitoring wearable that needs to run in fractions of a watt, or a translation system as a wearable in a commercial, in a consumer product, or a home gateway. There's a huge difference between the AI solutions that go between these things. Or an industrial anomaly detection system versus an autonomous agentic operating system for the factory. So at the end of the day, it is not about the TOPS, but it's about the solutions that you're going to build with it and the systems that you need to design around it to make it super effective. Now, we all know this, and this is nothing new. As we build any system, you need to design for the use case. The requirements are important. But why is it different for AI? The typical challenge is AI was built in isolation, and now you try to integrate it into a system and make it work when it was not thought through from the very beginning. So let's break it down. First, let's look at the application needs. And when you have data, we need to think about whether this is time series data, whether this is multiple camera feeds that are coming in. In a use case, are you doing anomaly detection? Are you building an agentic system? In a safety and security, this is super important, and we need to make sure that the AI and the decisions that AI makes are the guardrails needed around it. Do we need to build a different infrastructure for safe systems? And software, the longevity of the software, the upgradability of the models. We have to think through all of these, and you cannot retrofit on a system that's already built without it. Now, as we solve these application needs, now we run into the realities of the physics and the economics of scale. And there are three paradigms here: power, latency, and cost. And we need to be super aware of all these dimensions of the problem, and in many cases, one may dominate over the other. So it's very important for us to understand how these play against each other as we build the system. So at the end of the day, AI at the edge is about system balance. Are we truly able to build systems with the right trade-off and balance between all these parameters and constraints that are in front of us? And as you heard earlier today as well, it is a continuum. It is about a continuum of products that we need the society and the industry to build. But the semiconductor solutions and the platforms that go into it are very, very different. You can never put a humanoid brain into a small hearable. So there is a huge diversity of portfolio needed. And from a semiconductor vendor perspective, it is not about one product portfolio. It's a diverse portfolio that spans across various types of families, fit-for-purpose applications, and the other technology, other technology building blocks that need to go around it. So this continuum is super critical for us to achieve scalability at the edge. Now, here I'm showing the NXP expansive portfolio available for you to start building such a product, such an expansive continuum. You start with the MCX or the MCU, which is the entry-level products that we have. They usually comes with complementary analog circuits that allow you to build very good factory automation or low-level applications with AI built into it. And it could be anomaly detection, it could be based on time series data or other classification projects or RNN type of products. Now you go up the continuum, you have now a RT or a crossover MCU, which is a hybrid between a lower-end MCU and an application processor with real-time processing available. And in this portfolio, we bring in a higher class of AI, which is now able to deal with CNN type of models. And you're able to achieve low power wearable for glasses or other types of products. So you're achieving much higher performance of vision use cases or factory automation use cases, but at the power level of an MCU. And then you go up further. You have the full-blown application processor portfolio, which spans industrial, automotive, and other segments that we can use these for. And here, we bring in the Gen AI capability. And so now you can go from, with some of these application processes, you can go from low-level training, low-level time series data all the way to generative AI-based applications. And recently, we've added now discrete NPUs that complement the application processors. Now you're able to scale the AI performance even further without changing the host processing or the software in the host processor. So this allows that scalability now go to a different level, bringing more and more generative AI capability. Now, no portfolio is complete without software. So we have a whole suite of AI software ready that complements the hardware portfolio that we have. For anomaly detection and time series, we have EIQ Time Series Studio. And then you go up one level up for CNN and modifying the models, quantizing and optimizing these models for the edge. You have the AI toolkit and the model creator. And then you have, for Gen AI type of workflows, the EIQ Gen AI workflow. And then on top of all of this, as you build systems with many types of AI solutions, you could put together an agentic workflow, which is more of a system-level optimization that is possible. So now I'll talk more about this as I get more into the use cases coming up. Now, what I want to do is pick 3 examples that illustrate the diversity of the edge and what we can offer you, which provides that breadth of coverage that you need to build your products. I start with the lowest end or the entry level, as you would call it. And motor control is the basic building block of any industrial automation. And there are so many motors, all kinds of motors, and we have the traditional strength in NXP to do MCUs for motor control. And imagine an industrial factory, and one of the plants and the motor goes down. This motor failure could cost thousands of dollars a minute. So the name of the game here is to detect these anomalies early on and prevent these from happening and manage the downtime for the factory. So what happens here? So we are able to layer in the traditional control loops in motor control with an agentic or with a AI-based intelligent adaptability as a hierarchical layer. And so what this allows is the fast inner loop is able to keep up with the fast control and deterministic directions of the motor, and then the secondary loop is able to manage these variations and the anomalies as they happen. What we have seen also is that in some cases, the behavior of the motor can also lead to secondary results. Like, for example, in an HVAC system, we've seen examples where the torque of the motor and the detection of the torque helps to detect whether there's a block in the HVAC system. So you can also use the same philosophy to make synthetic sensors that deal with secondary problems that can arise out of the system that you're building. And so for this, typically cost is the dominant factor because you want to be able to build these in low-end MCUs, but latency is a secondary factor. But for sure, latency is usually handled outside the AI system. And then we provide you the MCU, the toolkits for the Neutron, as well as the Time Series Studio, which allows you to work through it. Now, getting a bit into the tool flow, we have two distinct types of tool flow. One where you have just the data, not the model, and the toolkit allows you to prepare the model and make an executable that then can be integrated into the products that you're building. If you have a model already and you just want to fine-tune it with the data that you have, this flow also allows you to do that. At the core, you have an AutoML engine which allows you to pick the right model that is appropriate for you and your application, and it allows you to build hyperparameter tuning and the optimization within this toolkit. The biggest benefit is that it simplifies the tool flow, and for a lot of the embedded engineers who are not familiar with ML, this is a tool flow that is a perfect fit because you don't have to get into the dynamics of data curation and ML optimization, and the tool hides it from the user. Now, you get to the next level up. We get into use cases where you have a human-machine interaction. Speech is the normal mode of communication for human beings. So when you have more and more cobots and robots in our mix, it's no different that you expect the communication to be based on natural language and speech. But the problem is, this is not just about speech-to-text conversion. Imagine an industrial setting. It's very, very noisy. Wake words don't typically work. And you may want to have much more complex layering of usage where you want to detect if the right person is interacting with a robot. You are able to detect other complex scenarios where you only want the robot to interact with something that is within a certain proximity. So you may want to have a UWB-based proximity detector that is a sensor into the system. Or you may want multiple cameras that detect the dynamics of the person that feeds into it. So this system allows you to build a scalable solution, either based on speech alone or speech along with different sensor modalities that are available to you. Here, latency is the key factor, because imagine in many situations, you want to communicate to the machine and you want to be able to stop when a certain hazard happens. And even half a second of delay might be too late. So it's super important to optimize the system for latency. And here we also bring in with, you can just do an IMX RT portfolio if you just want to stay in the speech domain. If you bring in vision and more complex multimodal scenarios, you bring in the Gen AI workflows that I'm going to talk about now. This is a full-blown workflow where you could have the person being detected from a group, and it only reacts to people who are authorized to communicate with it. It only reacts when it's pointing. You could train it to only react to systems when you're pointing to the machine. You could have various modalities that are built into it. And so the attention front end that I'm showing here deals with when the speech-to-text needs to be triggered. So speech-to-text will not be triggered until it meets the criteria that you've defined, whether it is proximity-based or the user-based, or you can even layer in another level of authentication based on the right usage of the system. Now, the output is an audio and a video feed that goes into the perception stage, which then does the speech-to-text conversion. But along with the speech-to-text conversion, what's happening is there's a VLM running which gives context to what's happening around it. As we know, in most communications, when even human-to-human communication, half of what is intended is not in words. So you have to really understand the context of what's in the room and the environment at which these words are being communicated. So the VLM really provides that multimodal context setting that then feeds into the thinking and reasoning stage, where you have an LLM running, which takes decision based on the inputs received. And then at the last stage, you have the action stage, where it either responds back in a text-to-speech conversion, or it takes further actions. Now, this is a very complex flow, and we are able to split this or combine this depending on the system you're going to deploy. So this shows the scalability that we're building in. So you could either just have the attention front end and the perception and not have the others, because the others may be integrated into a different system. Or you could have each of these built in. So you could bring in just an IRATOM X95, or as you have more stages built in, you could add a discrete NPU to it to bring in more LLM capability and intelligence capability at the edge. This shows the scalability that's needed in some systems. So when you build a portfolio, you may have a lower end where you just want to stay with speech, and as you go higher end, you bring in other multimodalities, and you may bring a higher end system which has much more capability and scalability without having to redesign it again. Now, the third example, which is the more complex of the three, here we are talking mostly about the action stage, right? This is about a robotic action or a AMR which has to operate under very strict thermal and power envelopes. So in most of these cases, you want the best performance you can get, but you have so many rules and constraints about the battery life, the power that is available to the robot, and other criteria. So I'll take one specific example of an in-home assistant robotic arm. This is a very interesting example because an in-home robot is very different from an industrial robot in the sense that the power available to it may be very different. You won't have industrial-grade power systems feeding into it. It needs to operate at a different noise level. You have the safety conditions that it needs to operate under may be very different. Imagine you're a robot with a knife. You need to make sure it's safe around people around it. So the safety guidelines that you need to put around it are totally different. So this is the kind of infrastructure that we are able to provide, which allows the OEM to decide what level of capability you want to build. And here again, you can start with an IRATOM X RT. You can add an application processor or scale to an application processor and build in the discrete NPUs as you need more and more intelligence. Now, here we talk about VLA. Normally, you hear about VLAs in the context of very high-performance systems. I'm here to show you that this robot that you're seeing, it's running on an application processor with an integrated NPU. In this particular video that you're seeing, it's a VLA, sub-billion-dollar parameter VLA that we are able to stage in a different way to make sure that you're able to run this within the thermal envelope of a robot like that, under the compute performance of something that you can handle easily in a tightly constrained environment. What we have done is we have staged the VLA into a vision encoder that then maps into an LLM, which then maps into an action expert. And by doing all of this, we are able to manage the workload in such a way that it's able to run within the capabilities of a discrete NPU. Now, imagine where you go to the next level. It's not just about individual devices. You have a system of AI devices at the edge. And now the job is different. It's not about optimizing each device, but it's about orchestrating a set of devices. You need to make it may vary from just monitoring to data movement to agentic coordination, path planning. There could be immense possibilities on what you want to do at a system level with a set of independent robots or independent systems. So I'm going to start with a simple example. This is an AI-generated image, just to illustrate the point. You have a factory where you have a factory here where it's supposed to be a video. Okay, it's a factory where a fire happens, and then the whole point is for the system to detect the fire and do something when it happens. So what we have here is a multimodal agent where you have a perception agent which detects the fire or associated with the sound that comes with it, and then it passes that information to an orchestrator, which then can decide what to do with it. And what I'm trying to show here is that even though the intelligence is mostly in the discrete NPU, the i.MX 9.5 can run an agent, provide the LLM information to the RR discrete NPU to get a recommendation of the action, and then the action could be to turn off a sprinkler or to close a valve, and that's executed through an MCP interface into an MCU, which normally does not have agentic capability. So with an MCP protocol, we're able to integrate an MCU together with an agentic application processor, achieving a total agentic function. So this is, I would call it the basic building block. But now you scale it further up. And in a normal system, it's far more complex than that. You have a system having many robotic arms, turbines, AMRs, and quadruplets. And the job here is to orchestrate between all of these and make sure that the overall system can be coordinated seamlessly and executed within the guidelines and the rules that you set. So you have the AI agents running in the AI hub, being able to manage each of these machines, which by themselves are AI capable, but they are not agentic. So they are able to, but using an MCP and agent-to-agent communication, the AI hub is able to coordinate the actions needed between them. Now you take it one step further again. This is a real engagement that we have going on with the medical system integrator, where we showed at CES the capability of some of these machines, like we had anesthesia machine and a neonatal monitoring system using agentic capability. And what now we're doing is we have a central orchestrating agent deploy or being set up in a hospital where it's able to monitor a patient's movement across the various systems and collect the data. And in many cases, it's just about collecting the data about a particular patient or a particular scenario. And then you could later decide if you want to take some actions on it or flag it or send a flag to a doctor or a medical service provider. So now, as you can see, you go from each of these systems being built with AI capability into a layered ability to manage a system altogether in an agentic way. So what we provide here is an agentic framework which is totally scalable. You have an orchestrating agent, and then we provide a containerized platform into which you can integrate your own agents. You could bring in agents that you may have in the cloud and try running it on the edge on a discrete NPU. And you could have an MCP tool that coordinates and controls motors or other machines that have the MCP capability in your system. The beauty here is this is based on an open framework, and it uses industry standard protocols that you can mix and match with the agents that you get from the cloud or from other machines that you're able to integrate into it. And by having a containerized capability, you're now able to put guardrails around agents like OpenClaw and not let it access things that you don't want it to access, right? So now this shows you that this basic framework can be scaled across one device or a set of devices because this works based on standardized industry interfaces that have been defined. So I'm going to now close here, but what I'm trying to show here is that NXP is able to show you that the agentic AI capability that you need at the edge varies from small machines to the very largest systems which need agentic orchestration. And we provide you the tools and the software tools as well as the hardware infrastructure needed to build these kinds of complex systems. And I go back to our foundational theme. It is not about the raw tops. It is about what it is used for. And if you're really being smart about how we implement these systems, we can do a lot more with constrained tops within the envelopes of power and performance that we can afford. And then together, I think it's very important that we look at systems in a completely different paradigm and how to build safe, secure systems that allow us to scale across the edge without depending on very expensive machines or very power-hungry and very expensive cloud models. So I end here. Thank you for joining. And we have our CEO, Rafael, presenting tomorrow at a keynote. And he's going to talk about future-looking visions for AI and intelligence at the edge. Thank you.